Okay. So this theorem we did yesterday, right? So this is the product formula for this phi of n. So it is yes. So this one is fine. So next we have few more results. Let us see that. So the Euler's totient function has the following properties. So the first one is that the phi of, suppose p is a prime, and if I have p power a, then it is nothing but p power of a minus p power of a minus 1 for prime p. And the condition on a is greater than equals to 1. Right? Okay. So yes. So any idea how to do it?
For example, phi of 3 power 3, phi of 7,
Yes. 7 is any. Yes. You take some higher power.
3 power 2. Yeah.
Yes. 3 power 2. So this is phi of 9. What is phi of 9? Phi of 9
5 of
in, I think,
9.
calculated, right?
Yeah. Is
Mm,
equal to
yes. Phi of 9 is 6. We calculated, right? Phi of 9 is 6, right?
k equal to 1 to 1 to n. This is it.
6, right? Phi of 9 is 6. And if I take the formula,
Is it
what the,
because 1, uh, 2,
hmm,
3, not 3, 4,
hmm,
5,
hmm.
7,
7 and 8, right?
1, 2, 4, 5, 7, 8.
Okay.
Mm.
So phi of 9 is 6, that is fine. And if I take this formula, that p power a minus p power of a minus 1, so it is 3 square minus 3, right? So that is also 6.
Yeah, yeah.
Right. So, but how to prove it? So yes, we'll use the yesterday's formula. So phi of n is nothing but n times the product of all primes that divide n, 1 minus 1 by p. That we saw yesterday, right? So here n is your p power a, right? So then what will be the product? So p power a, if I write here, so this will be p power a times what?
Pi of PA, uh, BP,
Yes, yes. How many terms will be there in the product?
2B. So 1 minus 1 over B,
Right.
and 2 time, n time, 8 time is right.
No, no, no. It is so. This is the product is only our distinct primes, right? So there is only one prime,
Yeah, yeah, yeah. So yeah, only one,
right?
one.
So yes. So this is nothing but p power a times p
Uh,
minus one over p, right?
uh,
So p power of a minus one times p minus one, right? So that's why p power a minus of p of a minus one.
uh,
Okay.
yeah.
So this first one is fine, right?
Mm.
Okay. So the next property is that phi, this phi of mn. So if it is product, so this is nothing but phi of m times phi of n times uh, d by phi of d, where this d is the GCD of m.
Hmm.
So this is the formula.
Oh.
Okay.
Yeah, yeah,
Right.
yeah, yeah. Hmm.
Okay. Let us see how to do it. So the thing is, note that each prime divisor
Hmm.
each prime divisor of mn is either a prime divisor of n of m or of n, right? Right. So what does it mean is that if p divides mn, so that implies p divides m or p divides n, right? So that is what we write, right?
Uh, is prime divisor of m multiply with n.
Right.
Either prime divisor of m or n. Yeah.
Right. So this is one case, and another case is, and there are prime, and those primes which divide both m and n. So there are two type of primes, right? So it either both m and n, right? So there are two type of primes. One prime which divide one of m or n, and there can be other type of primes which divide both m and n, right?
Hmm.
So if p divides m and p divides n, so this implies that p divides the GCD, right?
Hmm.
Right. Fine.
Hmm. Hmm.
So what we can do is, now we'll apply the formula. So this phi of mn, this is mn times p divides mn 1 minus 1 by p, right?
Hmm.
Okay.
Yeah, yeah.
So
Hmm.
from here, what I get is phi of mn divided by mn is product p divides mn 1 by 1 minus p. Okay. So now we will focus on this part.
Hmm.
P divides mn 1 over 1 by p, right? So this I can write like this and tell me if it is correct. So it is product of all primes that divide m, that is 1 over 1 minus p,
Hmm.
times the product of all primes that divide n, 1 over 1 minus p. But here there are some primes that can be dividing both m and n, right? So that is counted twice, right, in the numerator.
Oh, yeah, yeah.
Right. So
Uh,
that's why we have to divide that extra term. So p divides the GCD
mm,
of m comma n 1 over 1 minus p. Fine.
yeah, yeah, yeah. Is it okay? Mm-mm.
Yes, up to this part is fine. Okay, but if you see the first term, so if I see this first term, so this is nothing but phi of m by m, right?
Phi of m divide m.
Because this is our definition, right? So where is that? Yes, this one, right? So this is the formula we learned. So here, if I take this thing, so phi of n divided by n. So if I bring this n here, so that is nothing but the
Mm.
product of the primes, right?
Ah, ah.
Yes. So this
Mm,
part I can replace by phi of m divided by m, right?
uh, uh,
Okay.
yeah, yeah, yeah. Mm,
And the second term is also like this, phi of n divided by n, and the denominator is phi of the GCD, right? So d is the GCD divided by d, right?
mm,
So d is the GCD of m and n, right?
mm, mm,
Right. But this thing I know that it is phi of mn divided by mn, right?
mm, mm,
Okay. Now we have to just simplify. So if I simplify, so you can see that this mn and this mn n will cancel, right?
mm,
These things will cancel. So what I have is phi of mn is equals to phi of m, phi of n divided by this thing. So if it go up, it becomes d divided by phi of d.
mm,
So this is what we wanted to show.
mm.
Okay.
Yeah, 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 it's okay. Mm,
Right. So this is one result that we got. Okay. So the next part is a special case. So part C is if the GCD of m and n is 1, then this phi of mn, it is nothing but phi of m times phi of n, right?
mm,
So if d is 1, so this part will vanish. This part will become 1, right?
mm, mm. Yeah, yeah. Mm,
Right. So this is fine. Then the fourth property is if a divides b, then phi of a divides phi of b, right?
mm, mm. Oh, oh. A divided by B. Mm.
Okay.
B, B, yeah. Mm.
Yes. How will you do that?
So, from definition,
Yes, from definition, how to do?
A divided to B,
Hmm.
A divided by B, A divided by B, uh, A divided by B. So we give the definition of phi I and phi B.
Okay. But how will you show that it divides?
Uh,
Okay. So we
and
can
we
start
have
like this.
product. We have product.
Yes, we'll use the product thing. So
Product.
a divides b. So b I can write it as some a times c, right?
Yeah. Mm,
Right. So then phi of b is nothing but phi of a and c, right?
mm, mm. Yeah.
So
And
now by the previous property,
yeah.
it's phi
Phi.
of a,
Okay. Yeah. Yeah.
then times
Mm,
d over p of d, where d is the GCD,
mm, mm, mm,
where d is the GCD of a and c, right?
mm.
Okay. So then how to get means yes. So how do we have to prove that this part is an integer, right? This
Yeah.
part is an integer. We have to prove, right?
Mm,
Okay.
mm. It should be. We check is integer. Yeah. Mm.
Uh, okay. How will you prove that?
Phi C, Phi D, and D.
Yes. So here the thing is since this we have that c is between yes c
C.
is between one and two. Okay. So here we'll use induction on b to prove it. Okay.
C should let down A.
No, no, C is less than B, right? Because the product is B. Because C can be more than, because, for example, if you take B equals to 6, then it's 2 times 3, right? So C can be 3. It can be more than A, right?
uh,
The C is relation with only B. C has to be less than B. That is fine.
Let n be, that's fine.
Yes. Less than A, you cannot say because it can be bigger than A, right?
Okay, okay, okay. I missed the modular. Yeah, okay. Yeah.
Right.
Mm-mm.
Okay. So we'll prove the result by induction. Induction on B.
Understand. B.
B. Okay. So if B equals to 1, then we have it holds trivially because then A and C both are 1 and this is true. Now we'll assume that it is true for all integers less than B. B equals to 1 is true. So suppose then that this result D holds for all integers less than B, right?
Mm.
Now, since your C is strictly less than B, we know that it holds for C also, right?
Mm.
So now we know that so this D holds for C, holds for C. Now, since D equals to the GCD of A and C, so this implies that D must divide C, right?
Mm.
And since the result holds, so phi of D must divide phi of C, right?
Mm.
So okay, so from here I get that this is an integer. So this implies phi of C over phi of D. So this is an integer. So this implies phi of B equals to phi of A times this is D phi of C divided by phi of D, and this thing belongs to integer, right?
Mm.
So from here I can say that phi of A divides phi of B.
Mm. Mm.
Right? So
Mm.
now from induction it is true for any B.
Mm. Wait. I check a little bit. B1,
Yes.
2. Mm. Let them be. Yeah. Let them be. C. Let them be. C. Let them be. So therefore, for C, that mean the GCD of IC phi phi A. Here phi D, not phi I, phi D, phi C.
Right.
Phi C divided by the integer, the integer. That's okay. That's okay, but
Yes.
the induction
Yes.
here is b equal to 1, b less
Yes.
than
Yes. We prove for one and we assume for all integers up to B.
b, not
Right.
check for b is right.
Yes. Next we are doing for B. Right. Next step is only B. For B we are doing. So since it is true for all integers less than B, so for C we know it is true because C is less than B.
But we induction on b equal to b.
Yes, yes. So this part is for B, right? Because what I have to show. So if B for phi of B, I have to show that it is divided for phi of A divides phi of B, right?
Here for b.
So here actually we simplified to check what we have to show, right? So this is what we are proving, right? Phi of A divides phi of B.
Yeah. Phi c over phi d is
So
yeah.
this part is the we are using the induction hypothesis. We know that it is true for all integers less than B. So for C it is true, right? So since it is true
Mm,
for C, we can say that since D divides C, phi of D divides phi of C. So that is
mm,
the hypothesis, using the hypothesis.
C is less than okay. Yeah, okay, it's okay.
Right. So up to here, we are using the fact that it is true for C. So
Mm,
now we are seeing that, yes, so this part is an integer. So from here, I will directly say that this part is also an integer. So phi of A divides phi of B. Hence, the result is true for B equals to B, right? And yes, so it is in general, it is true by induction.
mm. So the hypothesis is the whole for all integer c less than b.
Right.
Yeah. Yeah, okay.
Okay. Right. So the next property is,
Mm.
so the next property is phi of n is even for n greater than equals to 3. Moreover, if n has r distinct odd factors, odd prime factors, then 2 power r divides phi of n. Okay. So first of all, check this part. So this is even for every n greater than equals to c. So this at least from the table, what we did for smaller values, you can check that. Yes. For n greater than 3, you can check that all of them are even, right? So here all of
Even.
them are even.
Oh,
So that is one observation. Then what else we have? It is saying that right.
yeah.
Okay. So we'll divide the proof into two parts. So suppose n is a power of 2.
Mm.
So n equals to some 2 power alpha, where alpha is greater than equals to 2, right? Because n is greater than equals to 3, alpha cannot be 1, right?
Mm.
Now,
No, wait. Moreover, if n has a distinct odd from first then uh, yeah.
fine.
Mm. Yeah, it's okay.
Right. So up to this is fine. Then what you can say that if okay, so first we'll do the case where n is some 2 power something, 2 power alpha. Okay. So 2 power alpha means alpha has to be greater than equals to 2, because alpha equals to 1 is not possible, right? Because n is greater than equals to 3. We start from
Three. Mm.
right. So then, yes. So then we know that phi of n, it is phi of 2 power alpha. That is 2 power alpha minus 2 power of alpha minus 1, right? That is from
Mm.
the part A,
Mm.
first property.
Mm. Mm.
So it's 2 power of alpha minus 1, right?
Mm.
and yes, so this is even. So this is true. Okay.
2 and 2 bar alpha minus 2 alpha minus 1 equal to alpha minus 1.
Yes, yes.
Oh?
Which is
Oh, mm.
yes, this is true, right? Because from here, if you take 2 power alpha minus common, so it is 2 minus 1, right?
Okay, okay. It's okay. Yeah, yeah, yeah.
Right.
Oh, yeah.
So this is even because alpha is greater than equals to 2. So this is true.
Mm.
So now the next part is so if n has at least one odd prime factor, right? So if it has odd prime factor, then by definition or by the formula, I have this is n times p divides n 1 minus 1 by p, right?
Mm.
Okay. So this I can write like this: p divides n p minus 1 by p, right?
Mm.
Okay. Now this is nothing but n times. We can distribute the product p divides n p minus 1 divided by p divides n p, right?
Mm.
Right. Now if I combine these two terms, n divided by p divides n p and p divides n p minus 1, right? So
Mm.
now this part is an integer, right? Because here we are only counting the primes, the distinct primes, and n has all those prime in the factor, right?
Mm.
So this part will be an integer, so I can write it some c times n
Mm.
p divides n p minus 1, right?
Mm. Mm.
Where this cn is an integer.
Mm.
Fine,
Yeah, yeah.
right? But the thing is, but what is p minus 1? So if p is an odd prime, then p minus 1 is always even, right?
Mm.
So this quantity is always even because
Mm.
p. So we are assuming that there is at least one odd prime factor, right? So the
Mm.
product will be always even, right?
Yeah, yeah, yeah. Mm.
Right. But the thing is, yeah. So we proved that this is even. This phi of n is even. So that is fine. That is true for any n, right?
Mm.
So we showed for both. Now we have to show that the next case, that if n has r distinct odd prime factors, then 2
But
power r
we have
divided.
two cases. N equal to 2 power alpha,
Yes,
and n has at least odd from.
yes,
Mm.
at least a one odd prime factor, right?
Mm.
So these are the only two cases possible, right?
Why two cases for n power alpha? So this is 2 for. Why? Uh, That mean on integer greater than 3, we have only these two cases.
Right, right. Only these two cases.
Oh, a little one odd from factor.
Right.
But the second case including the first case, right?
No, no. First class they are disjoint, right? So at least one odd prime factor. So odd prime factor means like this, right? It will. So I can have n like this, right? So n equals to suppose 2 cube.
Okay, okay. You mean zero, zero, prime factor and at least one.
Yes,
Two
yes,
case. Yeah, yeah. The first case is zero out factor from
yes,
factor.
yes.
Yeah, yeah. Okay.
So these are the only two cases possible.
Yeah, yeah. It's binary divide. Yeah.
Right. So in both cases, I show that phi of n is even, right?
Mm.
So this proves our first thing, that phi of is even for all n greater than equals to 3. So now
Mm.
we have to prove the second thing, that if moreover if n has r distinct odd prime factors, then 2 power r divided phi of n, right?
Mm.
So that is also follows from here only. So that is follow from here. So what we get is, the second part is, so what I can write is phi of n is c of n times p divides n p minus 1, right?
Mm.
So if here, so there is r distinct prime factors,
Mm.
right? So for each of them, this p minus 1 is even, right? So
Mm.
from each of them, I can factor out a 2 from each of them, right?
Mm.
So each odd prime p contributes a factor of 2 in this product,
Mm.
right? So I can 2 power r will divide 5 because there are r distinct prime
Mm.
factors.
Mm. Mm. Yeah, yeah, yeah. It's okay. Mm. Mm. We can imply from previous proof. Yeah. Mm.
Right.
Mm. Yeah.
So these are the useful properties of this thing.
Mm.
Okay.
Mm.
Okay. So yes. So these are fine, right?
Mm.
Right. So the next section is, let's do the next page. So the next section is the Dirichlet product of arithmetic functions. So the previous in one of the theorems, we saw a relation between the phi function and the Mobius mu function, right? So we saw this one. So phi of n is summation d divides n mu of d times n by d. So this one relation we saw, right? But the thing is here. So here we can consider this is a function. This is a function, and this is also a function, right?
Mm.
Right. So in general, we can have this type of things. So d divides n. So here is some function of d, and this is some function of n by d, right?
Mm.
So where this f and g are arithmetic functions. So arithmetic
Mm.
functions we defined, right? Arithmetic functions.
Mm. Mm.
So the general definition is, so if f and g are two arithmetical functions,
Mm. Mm.
we define their Dirichlet product.
Arithmetic convention does mean positive value only is right. The main.
Yes, yes, it is going from the natural numbers to the real number.
The positive number to real number.
Yes, yes,
Okay. Positive number to real number.
yeah,
Mm.
this one, right? So yes, this one.
Mm.
So this is from this n.
Natural number to.
Yes, all positive. So that is the natural number, right? So it
Mm.
is integer, positive integers. So n to either
Mm.
real or complex. So real valued or complex value.
Real and complex. Okay.
Okay.
Mm. Mm. Mm.
Yes. So suppose we take f and g to arithmetic functions. Then we define their Dirichlet product.
That con the Dirichlet product.
Yes, Dirichlet product. This is the definition we are seeing. So the Dirichlet product to be, so it will be another arithmetic function. So the arithmetic function h defined by h of n is summation d divides n f of d times g of n by d. So this is the general form. So this is also known as convolution of two functions, or Dirichlet convolution.
Mm.
Okay,
But mm,
right?
what does it mean here?
No,
I mean,
so here we are.
we
Here
just
we are.
summarize something is right.
No, here is formally defining what is a Dirichlet product. So, for example, so this is a special type of Dirichlet function. So this,
Ah, 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 ah,
phi
ah,
of n is an
ah,
arithmetic function. This is an arithmetic function, and this is also an arithmetic function, right?
ah, ah,
So here we are giving the general definition. So if
ah.
for any function f and d, I can define their Dirichlet product to be like this. It will be another arithmetic function.
That's the Dirichlet function.
No, no, h is another arithmetic function. H is the Dirichlet product of these two functions, f and g.
Dirichlet product.
Right.
Okay.
So the notation we'll use is
Mm,
that h will write it f star g. So this is a Dirichlet product or convolution. So
uh,
h of n will be f star g of n, like this. So this is the notation.
uh, mm,
Okay.
yeah.
And we'll use capital N. The special arithmetic function is, so, or the identical arithmetic function, you can say. The arithmetic function n will use to denote n of n is equals to n. So it is the identity function in the class of all arithmetic functions. Okay. So then
Mm,
what we have is phi is nothing but mu star n, right? That is from our theorem.
mm. Phi equal to mu.
Yes, because that is what we saw, right? Phi of n is summation of d divides n, mu of n, and then n by d, right?
Uh,
Right. So if I so by the definition, this is only what we have, right?
uh, mu.
So
Mm,
this is what we have, right? D divides n, then mu of n times
uh,
capital N of n by d, right?
yeah.
But this is our identity function. So this and these are same.
N n equal to n.
Yes. So this is, you can say, this
N
identity
equal
function.
to n. Yeah. N. So the submission. Oh, the submission okay. We do not need to notation the submission.
Yes. So this definition is clear, right? So this is the general definition of the Dirichlet function or Dirichlet product.
Yeah.
Yes.
Okay.
So this is the previous thing what we obtained, and we can see that we can, in this notation we can write like this, that phi is the mu star n.
Mm, mm. Yeah, it's okay. Mm.
Right. So the next theorem is
Yeah, it's okay. We can stop here. Yeah.
okay.
I go to spot my office. Yeah.
Okay. Bye then.
Bye bye.